All right, well, here we go. Whoops. Let me get this started here. All right, can you, without me saying anything, can you remember anything from yesterday? What's something you remember from yesterday? Yes, Andrew.
Like the reason why water has hydrogen bonds.
Okay, and to be a little more specific, there's intramolecular bonding. That's what holds one water molecule together. Do you remember which one of those were? What kind of bond holds each water molecule together? They are covalent, and because they share but unevenly, we specifically say polar covalent bonds. Okay. Now the fact that it's bent and they're both are polar covalent bond makes the whole molecule polar. So do you remember which end of the water molecule is slightly negative? Which one do the electrons spend more time around, the hydrogen end or oxygen? Oxygen, because it's more electronegative. It's a fancy way of saying when we share electrons, they spend more time with me. All right. Then what you brought up was, what about the intermolecular bonding? Does water attract another water? What do you think? What was that called? Hydrogen bonding, okay? And yeah, it's not as strong as a covalent bond, but what if you had lots and lots and lots of water molecules all pulling on each other? You could make things like surface tension, and you could make water who should not. There's no way at room temperature water should be anything except a gas, but it's a liquid. The hydrogen bonding keeps it from turning into a gas. And our whole planet is full of water, isn't it? Your cells need liquid water to make all the ions move around so you can be alive. So anyway, that's why I think water is just God's special gift in the small molecule world. He has many gifts, but I think that's one for us. All right, then we jumped from that. What do you remember about this? Without me teaching it, what do you remember? Tell me, raise your hand and tell me something you remember from this picture. And that's what my demonstration's on, but what do you remember about this picture? Claire. Say it again.
Like not all water can conduct electricity.
What water can?
Distilled water.
So distilled water only has H2O in it. That's all. H2O, H2O. And that's a molecule. It's not an ionic compound. So if you just have water, there are no ions to move the charge from one side to the other to vary charge. What about tap water? It does? You think so? Just because I told you so? You said, and you think I'm lying to you? I try not to, but I'll actually do a demonstration today. So even if you thought I was lying to you, you'll say, hey, he's not lying to me. All right, so we'll do that today. Anyway, we're going to be doing a series. I'm going to do a series of about, 6 or 7 or 8 things, and I'm going to show you this little instrument we have. So let me get this book out of the way, without spilling anything. All right, so what we have, kind of a neat little thing here. And can you see this pretty well? I'm trying to get with no glare. Let me see if I can get no glare. Ooh, that looks pretty good, doesn't it? You like that? All right, this right here is called LabQuest. LabQuest is like a handheld computer. It's about $325, and we have our school owns about 8 of these. And I'll tell you what I really, really like about it. The company that makes these are very, very teacher friendly. I could call them up. I might even talk to the president of the company, and they're out in Washington. And anyway, Vernier is the company, and they make LabQuest. They make over 60, 70, might be 80 different sensors that can be plugged into this. So I happen to have today, I'm doing a thing called a conductivity probe. So this thing right here, all I do is stick it in liquid, and it will read a conductivity for me. And so this is better than just a light bulb coming. Hey, light bulb comes on, light bulb doesn't come on. See that? This is more quantitative, isn't it? If I want to do an experiment with numbers, I could do that. I could see a student, if they were careful, you could take something like some salt water and find out the conductivity of it, and then dilute it in half. exactly in half, like 10 milliliters of water, 10, and then find the conductivity, and then do it again, cut it in half again, dilute it again, dilute it again. That would be a neat little experiment to see what happens to the conductivity as you cut the amount of ions in half each time. Does that make sense to you? Can you almost picture yourself doing that? Okay, so here's what I'm going to do here. Even though I know you want this to read 0, I'm going to put this in some distilled water. So let me rinse off the probe, because I did some this morning. I can't get it absolutely 0. There's whether or not it's so sensitive, it could even tiny bits of things. I tried to rinse out the beakers, but I can get it close. So let's see how close I can get it. Okay, now I know that you're thinking, well, 3.6, 3.5, that's not 0, but it really is. When you see these other numbers, you're going to know this is really like 0. So that's about as low as I can read it with distilled water. So I'm going to say that's 0, and so distilled water does not really conduct electricity. All right, let's try another one. Now, if you want to make a little chart, I actually have some of these questions on the next test, but let's make a chart. And the first one was distilled water or pure water. Your book calls it pure water, okay? And does it conduct electricity? And you can say, well, no, essentially 0. So whatever number I got, what, 3.5, I'll consider that to be 0. We'll subtract 3.5 from all the rest of them. So we're going to say 0 for that. All right, next. Let's do tap water. What do you think? Why don't you give an estimate? If distilled water was 3.5, which is almost like 0, what is this going to be? Any guesses? Any guesses? 10? 20? Try it. Can you see what I meant by distilled water being 0? So even if I subtract 3.5 from this, it's still going to be about 165, isn't it? 167, I mean. So this is reading, well, now it's up there now. It's going to read about 170 if I subtract the 3.5 as my 0. All right, so what do you think? Distilled water, it does conduct electricity, doesn't it? Okay, I'll rinse that off. I'm sorry, distilled water does not, tap water does, my fault. All right, now, salt water. And again, does it matter how much salt? Yes, it would. I didn't actually measure this out because I'm just doing a demo today. But let's try salt water. What do you think? Top water is 170. What do you think about this guy? So it's about over 300, right? So even if you subtract the 3.5, about 306, something like 306. Okay, so if I can rinse that off. All right, sugar water. I'm sorry, did I say salt water last time? Yeah, that was salt water, right? All right, sugar water. Oh, by the way, when you put salt water, right next to it, put NaCl aqueous. If you put NaCl aqueous, you'll know that it was table salt. All right, there are thousands of salts, hundreds of salts. Yeah, this is sugar water. Now, sugar is C12, H22, O11. So what do you think? It dissolves in water because it has a polar nature, but when I put it in water, will it actually produce ions to help the electricity flow? What do you think? What do you think on this number? Let's try it. And it's down near the 0 range, isn't it? So even though it's reading about 4.9, again, there might be a little contamination in the beaker. It's essentially 0, so I would not expect sugar water to conduct electricity. There are no ions. It does dissolve in water because it's polar, but there are no ions to conduct electricity. All right, what about HCl? What about HCl? And all acids and bases are aqueous. Do you know that? By definition, they're solutions. So this, you can say HCl AQ, but all acids are solutions. What do you think? What is it in acids that, what kind of compound do you think it is? You ever thought about that? what is it that, when I put it in water, what makes an acid anyway? Has anybody thought about that? What makes an acid an acid? And so what happens is, why is it that when we write the name, the formulas for acids, why do we write H first? Because when you put this in water, it breaks up into ions. And this is the ion that makes you an acid. So HCl is going to have this ion and that ion. They should be all floating around. They're not together anymore. They're not together. They're actually separate. So what do you think? Should this conduct electricity or not? What do you think? So it's an ionic compound. And let's try it. Whoops, get down here. Over 300, right? So 315, if I subtract the 3.5, 315, something like that. All right, did you expect that? So acids, for sure, because they, by definition, they have ions, especially hydrogen ions, they have to conduct electricity. Let's do a base. This is called NaOH. Now, what makes the base a base? Well, for first year chemistry, I'm using sodium hydroxide, and when you put this, AQ, when you put this in water, you get sodium ions. That's not what makes you a base, but then you get the hydroxide ions. That is what makes you a base. Everybody see that? So bases also are ionic compounds, aren't they? And so, what do you think? What do you think is going to happen? Big number? Let's try it. And again, we're getting up there in over the 300 range, right? Okay, so very, very good conductor of electricity. I'm sorry, say it again. I think it was like 315 or something like that. All right, try some more. Here is some vinegar. What do you think about vinegar? If you can help me out a little bit, vinegar. I know the answer, but what do you think? Should this conduct electricity or not? Excuse me. Just take a guess, you know, say, yes, because, no, because. What do you think? Todd, what do you think? You like to think about things?
Say yes.
I love that. That's great. So let's draw that. Here's acetic acid. And again, why do we draw the H first? Because we know it's going to break up into ions, and the ion it's going to break up into is this ion. Who knows the name of that one? Who knows the name of that ion? Acetate and the hydrogen ion. So I do expect this to conduct electricity. If you were to take a second year of chemistry, you'll find out that there are acids that are called strong acids. Strong acids mean when you put them in the water, 100% of them break up into ions. HCl is known as a strong acid. 100% of them will break up. Vinegar has acetic acid in it. It's 95% water. Acetic acid is a weak acid. Not 100%. Only 1 out of 100. Only 1 out of 100 of these break up into ions. It's called a weak acid. So, I haven't done this one. First time I've done this one, but well, I'm kind of expecting maybe a lower number than I got for HCl. Let's try it. Not too much lower. That's similar, isn't it? So we do have enough ions in there to do that. Okay, so Todd, that's a good thing. It was an acid. All acids have ions in them. All bases have ions in them. All right, 2 more. Let's see, that was vinegar and HCl, NaOH. Okay, Powerade. I got some Powerade, okay? Why is it that doctors sometimes will say, if you had a fever, make sure they have plenty of electrolytes? And they say, you know, Gatorade, Powerade, even soft drinks have it. But what do you think? You think, am I going to get a good reading here on Powerade? Okay. And the kind of ions they have, sometimes the sodium ions, potassium ions, okay? Let's try it. Come on. You going to do it? Woo! Yeah, a lot of electrolytes in there, isn't it? I mean, this is an electrolyte. Electrolyte's a solution that conducts electricity. It's way up there. maybe about 308 by subtracting the 3. And again, it's hard for me to get all the contamination out of these beakers. And I happen to make some tea today. Now, I've never done this, but I made some tea. I use artificial sweetener, and I use tap water. So we'll see. What was tap water before? Was it one what? Okay, so if it's higher than that, that means there's something else, maybe from the tea bag, maybe even the artificial sweetener has some ions in it. Let's try it. Okay, it's not going past 300, but it is up there around 270. Yeah, if I subtract the 3 from it. All right, there's my tea. But anyway, we only have one of these probes, but like I said, we have a lot of different probes, but they only have one of these. So if you thought about it, you said, next week I'd like to do that. I have some time. I can come in at lunch. I could come in after school and have an idea. If you have an idea for a project, let me know, and I'll show you how to use it. What's really nice about this, once I plug that in, I turn it on, plug it in, it automatically recognizes which of the 90 probes I put in there. I don't have to tell it what probe it is, you know. Hey, it's not the thermometer probe, it's not the pH probe, it's not the dissolved oxygen probe, they know it. So they automatically recognize it and get it ready for you. Now, I'll show you something else you can do, and then I'll move on. We can also, with this thing, we could do show a graph, okay? And if I wanted to, I could, let's see. Let me see what I could do here. Oh, I need another beaker. Todd, go get me another little beaker over there. I'll do one more experiment, and I'll show you what you could do if you had another idea of an experiment. Okay, I don't know what that is. Okay. All right. Here's HCl. I'm going to put some NaOH in there. Okay. I'm going to put some NaOH in there, and then I'm going to add some acid to it. And what we're going to do is we're going to try to watch what happens to the conductivity as I do that. So I have base in there right now. I'm going to try to do this without spilling it. Now, what I'm going to do is you press this little button here, and it starts taking data. And can you see that little number there? I know I'm in your way, but let me see what happens. It's up there. Conductivity is pretty high, isn't it? Let's put some acid in there. Ooh, come on. Come on. Come on. What? Come on. You should go down lower than that. Ah, okay. I don't have any more. Ah. Is that door locked? No. Stay right there.
I mean, because you always get the lights. No. So what?
Okay. I think I know what happened. That the concentration of my base is high, the concentration of my acid is kind of low. Todd, go get me another beaker bigger than that, please. Now, I'll tell you, I'm gonna stop taking data for a minute. Oh. Go down to. Oh, it did go down.
You'll go down.
Oh, okay. Thank you. I'm gonna see if I can get it go down lower. I might not be able to. What I want to do is start taking data again. I'll discard that data. And here we go. All right, so let's try that. And I'm going to pour some acid in there. that's interesting. That's interesting. Try some more. That's not what I expected to happen. I may have to check the concentrations of these, but I want to show you. Probably stop this experiment. I think oh, there it goes. Ah. So what happened there for a while, if I had a lot of ions in here that were acid, a base, NaOH, what happens is when I put HCl in there, some of the ions lock together, and H and OH will come together and make water. So I thought what would happen is, and it happened on the first run, but instead of having lots and lots of ions, some of the ions will get tied up, and I'll have less ions. I expected the conductivity to go down. I may have to work on that a little bit. And then I started putting a lot more acid in there. I think that made it go back up, because I think I neutralized all the base, and it went past that. But the numbers are way up there. I'll have to try that again sometime. Okay. HCl. All right. Any questions on that? So if you can see, you could actually look at a graph here if you want to do it real time. There's another thing you can do with LabQuest. You could say, I want to do an experiment, but I don't want to do click time every second. I just want to take a reading and then do something to it and take another reading. I want to take a reading when I want to. And this thing can do that too. Instead of doing every second, it only takes a reading when you want it to. So then you could make a graph out of that. All right, let me get this out of the way here. All right. Yeah. Here. All right, any questions on that? You thinking about it? Just think about it. All right. So the other thing that happened yesterday, that was right at the end of the period, so we didn't really get a chance to talk about it, I think, was this right here. And I want you to take a look at this. Look at this equation here. Everybody see that? All right. Did we do that yesterday? Did we talk about that one at all? Okay. So in English, it says potassium chromate reacts with barium nitrate. Now, do you think something's going to happen? Do you think a reaction is going to happen? You say, well, it doesn't have to. Last chapter, as long as you could write it on paper, it probably looked like it was going to happen, didn't it? But that's not how chemistry works. You need this thing called a driving force. You got this beaker that's full of ions, 2 potassium ions for every one of those chromates, and there's millions and millions of ions in there, and you're going to put them together, and they're going to bump around. You get that? Let me ask you this. What happens when potassium ions bump into chromate? What happens when potassium ions bump into chromate? Why don't they make potassium chromate?
Doesn't it create like a yellowish liquid?
Make a what?
A yellowish liquid?
It is a yellowish liquid, but how come I don't see the solid? I don't see the solid potassium chromate. And I'll give you a clue. It's that word right there. When you put potassium chromate in water, what happens to it? It dissolves and the ions break up. So which one's greater? The ability of potassium to hang on to chromium, or the ability of water to pull them apart? Who wins? Water wins. And so even if these guys bump into each other, water will make sure they don't come together and form a solid. Same thing with this guy. So now, is a reaction going to take place? We don't know yet. But here's what I'm going to do. In your head, I didn't call Victoria. Okay, Victoria. In your head, what kind of a reaction do you think this is going to be? How would you classify it? You can do this. Say it again. If you had to look at it and you see AB plus CD, AB plus CD, what would you expect? What kind of reaction? Okay, that's fine. All right, we're gonna call you, I'm calling you, that's it. What do you think? You can do this. Single equation would be A plus BC. This is AB. Yes. Now, let's watch that. You do this, you do it. If it is a double replacement, in words, what are the two products gonna be? Say it out loud. Oh, you can't see that? Okay, I'll make it fine. Do you have your book with you? Okay. Let me magnify. Is that better? All right, so double replacement, give me the word, the name of one of the products. Still can't read it? Okay, wow. All right, that's one way to get out of the question, no. All right, you have a book? All right, what do you want to do? Tell me, what's one of the products gonna be? It's double replacement.
Yeah, it's gonna be, first.
Didn't we just have a test on this?
Did we?
I thought we did.
Yeah, no, we did.
Okay, come on, you do it.
It's potassium. It's like so hard to see, it's like glare.
Okay.
Is it potassium, potassium chromate?
No, potassium chromate is what I'm starting with. You told me it's a double replacement
No,
reaction.
yeah, I was asking, that's the reactant, right?
That's it.
Yeah.
Has a big old star on it.
Okay, alright. Oh, I was looking below the glass.
Oh,
Oh.
okay, here we are.
Alright, so it's gonna be potassium nitrate, and barium chromate.
Okay, you're right. You're right. Now, right now, that could happen, couldn't it? But it's not going to happen unless we have a driving force. Does anybody happen to know, if I turn this page, if you read this at all, and here's the next picture, is there going to be a driving force? Finley,
Formation of a solid.
what is it?
Formation of a solid.
All right, how do you know that?
Because I read head.
In your head?
I read a head.
Oh, okay, I was going to say, yeah, that's right. You know what? And so here, I'm going to show you a tool. I'm going to give you a tool now that you can use. And so everybody's going to get one of these. You give it to those two rows. You give it to these two rows, okay? Okay, so now I'm going to show you. Oops. I'm going to show you a chart, and a lot of chemistry books don't include this chart. They actually want you to memorize what they call the general rules of solubility. And so I want you to look at the chart here, and whoops, it's really magnified, isn't it? Let me go down here. Now, when would you use this chart? Number one, you would use it for a double replacement reaction. See that? That's what we have. And you only use it for the products. See that? So what we're going to do here is, Will, if you remember, can you remember the two things you said? What are the two products? Potassium nitrate.
Barium chromate.
All right, let's take a look. Now, we're going to look these up. They're alphabetical. All the cations are over here, and all the anions are over here. They're alphabetical. Let's look up potassium nitrate. Potassium and nitrate. Now, potassium nitrate, what's going to happen when potassium ions bump into nitrate ions? Who's going to win? Is water going to win, or is the potassium and nitrate going to win? Water wins. So even if they bump into each other, they're not going to form a solid. Let's look up the other guy, barium chromate. Barium chromate. Wait a minute. What's that mean? What's S mean? Solid. So guess what? Is there a driving force? And you're right, Finley. The formation of a solid. That is what's going to make the reaction take place. And if you did read ahead, And I asked you to read the first 5 pages. So if you did read that, now look, they're all bumping each other. And what's sitting on the bottom here? What is that? Barium chromate. And now I have a tool that will help me look these up, right? I can determine whether or not the reaction is going to take place. But what's floating around above it? Potassium ions. And so this would still be an electrolyte, wouldn't it? It's still got ions in it. So this is called a precipitate. A precipitate is an insoluble product. It's a product. It's insoluble. That means it's going to come out like a solid, isn't it? So an insoluble product is called a precipitate. So another name for this kind of double replacement reaction is called a precipitation reaction. All right, let's see who's Mr. Smarty Pants or Mrs. Smarty Pants, okay? Does anybody know what the fancy word is for the material that's above the precipitate? And this not in your book. I just want to know if anybody happens to read. Anybody? Okay. All right. First of all, I'm not going to put this on a test, but I had to learn the word supernate. And supernate is the liquid that's above the precipitate, and so that's called the supernate. All right, so anyway, what I'd like you to do is I want you to spend a little bit of time here, and I want you to look for general patterns. Okay, I want you to spend about 2 minutes looking at this chart. I'm going to give you one of them, okay? Let me give you one. Okay. And by the way, P, partially soluble, means that maybe a little bit dissolves, but a lot of it won't. So that would be maybe. So here's a pattern. All acetates, except for this one, all acetates except for that are soluble. Okay. You got another one?
No, I just have a question. Does the blank square just mean that there's like no reaction?
Right. It means that if it does form, it quickly decomposes probably, so you wouldn't expect that to form. That's a great question. Excellent question. All right, what's another pattern? Give me something else that is kind of a general rule about solubility. Finley.
Basically, if anything reacts with nitrate, it's going to be aqueous.
Okay, let's take a look. Let's look at nitrate. And I don't think you mean reacts with, you mean a salt. These are all salts. Salts are ionic compounds, right? So you say salts of nitrates. Wow. Every nitrate is what? All nitrate salts are soluble. What about barium nitrate? Soluble. What about sodium nitrate? Soluble. Iron nitrate? Soluble. And even though I'm going to give this chart to you on the test, if you remember certain things, it'll save you time. Get it? Okay. How about another pattern? Eloise.
Most of the chlorate salts.
One more time.
Most of the chlorate salts are soluble.
Chlorate? Okay, chlorate. Now, except for what? Antimony, bismuth. Ooh, there's a lot of exceptions there. Oh, you said chlorate. My fault. You said chlorate. Yeah, I like that. All chlorates are soluble. I love it. Yes.
All potassiums are soluble.
Wow, she's going this way. I like that. All potassium salts. Say the word salt, okay? I know you think the only salt in the world is the stuff on your dinner table. You get it? These are all salts. All right, Will, another one.
All sodium salts are.
Yes. Yes. And he even said it right. All sodium salts are soluble. Any others? I think there might be one more missing. Go down, go across.
All potassium salts are soluble.
Okay, we said that one.
Hydrogen salts.
Now, hydrogen salts are actually called acids, aren't they? I like that, though. He said all hydrogen salts are soluble, and you know why? Because those are called acids. All acids and bases, by their definition, they are solutions with those ions in it, so I like that. One more. Should be at least one more. Look at near the top. Ammonium. Look at that. Ah. Now, there are some other columns where almost all are soluble. So here's what the author of your book's going to do. The author of your book, they want you to learn the general rules. And let's see how many we already came up with just on our own device. See that? That they said one of the general rules is, what's the first one? Can everybody read that? It's hard to keep magnifying this. What's it say here? Almost all nitrates, and they are, all nitrate salts are soluble. Hey, we discovered that. Most salts of sodium, potassium, and ammonium are soluble. Hey, we discovered that. Most chloride salts are soluble. Yes and no, but look at the exceptions they had. Silver, lead, and mercury. See that? So they have 3 exceptions on it. So a lot of chlorides are soluble, but those are not. And you, Eloise, you said chlorate, right? That was good. I only see that. Did I see it on here? Next, hydroxides, except for those. So there are some exceptions. Now, in my opinion, I think it's fine if you want to memorize the general rules. What I'm going to do is give you this. And I have 2 things. I have the chart and I have the general rules. Everybody see that? If you don't find it up here, go down here. Everybody got it? If you can't find it on the chart, look down here. All right, so what I'm going to do here is I'm going to give you a real life situation. And okay.
So you said the chart, solubility chart, you said we only use it for products and double replacement.
Yes, you only use this for a double replacement reaction, and I only use it for the products. It's for me to predict a precipitate, which is going to be the driving force, right? Hey, what would happen if both products would have been soluble?
There's stayed in aqueous mixture.
And anybody?
Probably wouldn't have reacted.
And that would be a big old NR. So what happens if both products are soluble?
Won't react.
No reaction. See, last chapter, as long as you could write on paper, it was reaction, wasn't it? That's not the case. So we're learning a little bit more about what makes a reaction take place. Yes?
So we'll have this, like the.
Oh, yeah. And again, even though there are some chemistry teachers that said you need to memorize the general rules, I don't have you do that. I'll go ahead and give you the tool. Everybody got it? I'll give you the tool. Now, here I have 2 chemicals, and what I'd like you to do is I would like you to write out the entire balanced equation for this reaction. Are you ready? You're going to translate, okay? I'm like a Latin teacher or something. I'm going to say it in English, and you translate it into Cheminese. Lead 2 nitrate reacts, maybe, with sodium iodide. Do you expect a reaction to take place? And if a precipitate occurs, which one is the precipitate? One more time. Lead 2 nitrate is going to be allowed to mix with sodium iodide. All right, so write out the entire balanced equation. We just had a whole chapter on that. We should be able to do this. Lead 2 nitrate is going to be mixed and maybe react with sodium iodide. Let's see how well you did. Oh, I should have said they're aqueous solutions. My fault. Aqueous solutions of lead 2 nitrate, AQ. Did everybody get that far? It's going to react with an aqueous solution of sodium iodide. Is everybody that far? Yes? Can you do this without my help, right? Okay, go ahead. Predict what the products will be. Use your chart and put either AQ or S after it to tell me whether or not it's going to be aqueous and I won't see it, or S, I will see it. All right, is everybody this far? All right, now, I need to put something after this and something after that. Now, on a test, that's next Friday, I have about 7 in a row like this. And I'm gonna ask you, here's what the question says. If a precipitate forms, write out the formula of the precipitate. That's all I asked for. In this case, I'm gonna have you write the whole thing out, but on the test, I might say, if a precipitate forms, write out the formula of the precipitate. Now, I'll show you real quickly. Here's a quick way to do it. The two products in my head are lead 2 iodide and sodium nitrate. Well, all sodium and all nitrates are soluble. Why are you spending time looking them up? I know they're going to be what? They're going to be AQ, aren't they? And again, the more you remember, you don't have to look it up. Now, lead 2 iodide. Lead 2 iodide. Now, it looks like lead 2 and 4 must act the same. Iodide. What do you think? Again, partially soluble means that I still will see a solid. Maybe a little bit dissolves. So I'm going to put a big old S here. Now, before I do the experiment, I hereby declare I believe a reaction is going to take place, and I believe I'm going to get a precipitate. Let's try it. All right, sodium iodide. There we go. A bunch of ions in there floating around. Here's some lead 2 nitrate. A bunch of ions. Oh yeah. Oh yeah. So your prediction was that there would be a reaction, and the driving force would be the formation of a solid. So which one of these two is that yellow solid? Which one is the yellow solid? Okay, so there's my precipitate right there. And this way, when I was in chemistry in college, they made us put PPT, but you know, S is what we put in this class, okay? Okay, now, I'm gonna show you one more thing, and then we'll be done for the day. And I do want you to have a nice weekend. I would take my chemistry book home. I would try to do, you know, maybe 1 through 21, 1 through 19. I would try to do those. I'm gonna show you the next thing I'd like you to do. This is skill. And this is called the chemical equation. And your book likes to call it the molecular equation. I don't like that, but I'm okay. That's what they call it. So that's the regular old balanced equation, okay? Now, what we're going to do here is going to be the longest equation you'll ever write in your lifetime. It's called the complete ionic equation. Now, the complete ionic equation is tell me the whole story about ions and everything. And this is why I told you this chapter is definitely an honors level class, because watch what happens, right? What's actually in this beaker? This is all balanced, right? Did I balance it? Okay, what's in that beaker right there? Tell me. It's not lead nitrate. What's in that beaker? What's that say? There are lead 2 ions in that beaker? Aqueous? They're dissolved in water? Yes. What else is in there? Nitrate ions. Ah, watch, careful, be careful. For every one of those, there's what? Big old, see? No, I don't put diatomic nitrate, no. So there's one lead 2 ion and 2 nitrate ions, and you have to have the charger because they're ions, aren't they? Now we keep going. What's next? See if you can go ahead of me. Go ahead of me. You tell me what's next before I write it. You can do it. Just tell me what's in the speaker. Watch. I'll show you how Kieran. Kieran, your head's up, right? What? Go ahead. Tell me what's in there. You can do it. You can do it. What's in that beaker? What's that? Sodium what? Sodium metal? Starts with I. Starts with I. Sodium ions, right? And are they dissolved in water, Kieran? Are they dissolved in water? Yes. Now wait now. You have 2 of those, so I had to put a 2 here, don't I? So there are 2 sodium ions. Keep going, Kieran. Okay, what form? Starts with an I. Right. And what charge? Yes. And do you just have one of those? Is it dissolved in water? Yes. You just have one of those? Because you had 2 sodiums. 2? You're right. You're right. We'll keep going. Let's keep going. Let's do this one. Let's do this part first. Ready? Who did I? There must be somebody I didn't call on yesterday. Who am I? Hey, point to the person I didn't call on yesterday or today. Point to him. Everybody, point to him. Who? Oh. Okay. Julie, you help me. All right, ready? I'm going to do this chemical here. Ready? What are you going to put down? 2 sodium ions, 8 dissolved in water. Keep going. Nitrate, yes, yes. Okay, very good. Now wait, hang on. Somebody else is going to finish the story for me. We got about 1.5 minutes. Who thinks they can finish the story? Raise your hand and say, I'm feeling pretty confident today. Who wants to finish the story? Oh. Olivia. What is it? PB by itself, PB plus 2, PB 0, what do you want? What do you think? Hey, everybody listen. This is where people make mistakes. Watch. Watch. You know what? You said, oh, I understand, but why didn't I break this up? How can I didn't break that up? That's my driving force, isn't it? All right, wait. We're almost done. This is a fun part. Now we have the net ionic equation. All right, net. Ready? Now, what I'm going to do is I'm going to take away, and if you read the book, I'm going to subtract the spectator ions. What? What's a spectator ion? Well, it means that they didn't change. They didn't do anything from the beginning to the end. Watch here. Ready? Scan. Hey, there's 2 nitrates. What did you do? Nothing. We just sit around watching. Any other spectator ions? 2 sodium. What do you do? Nothing. Okay. So what's the net ion equation? What's the only chemistry that took place? Lead 2 ions bumped into what? Iodide ions and formed what? Lead 2 iodide. Whoa. That's the only chemistry that took place. All right, thank you very much. Thank you for waiting a couple of minutes. Thank you. That helped me.